have not gone far enough. So let me just recapitulate this as a references. But again, coming back to the Gordon scheme, why volume integrals? So we will learn that finite differences you can go to higher radicals, frequency code goes up to 6 radicals. And even higher, I think they have schemes for that. But if you land in shocks, your derivatives blow up. So any physical situation where you have shocks, you need to introduce artificial viscosity. If you are having artificial viscosity in a system, then things are driven by non-physical items, which you would like to avoid. So a nice alternative to that is the volume integral scheme. And as Pratik has been mentioning since yesterday, why is this important? Because it's useful because you are working in integrals, the conservation relation. So that makes the scheme very useful for this. So conservation relations are preserved. Mass and momentum are preserved. It's supposed to be preserved emission accuracy unless you mess up something. Unless you know source stuff. Many of the schemes, and again, tomorrow in a short lecture, I'll discuss when looking MHD schemes was you need to add source terms to your momentum equation and mass equations. But if those source terms are not there, conservation relations are good. It is second order equilibrium. Higher order finite volume methods are available. It has been implemented, but right now the one that is available is second order. So if everything is nice and preserved, where is the source of errors? We are saying that mass is conserved, momentum is conserved, everything is nice, shocks are well resolved. The errors come when you actually try to compute the Goldbach classes. Since Pratik has already introduced this, I will take the liberty to just say what the class is. So you heard the word about the linear amount, right? At the interface of two cells here. Let's say it's a black box for you right now. While doing that, you can do it analytically for simplified situations. For complex systems, you have to do it right. As soon as you go to numerical domain, you have to make some approximations. So therein where the accuracies are sort of lowered due to the assumptions you are making. Fine. So again, this is you have gone through these set of equations in Pratik's slides. I'll just recapitulate because I want to use this to introduce what is the limit. So we start with a simple 1D conservation relation. Okay. And this is the structure of our volume element. In finite difference, what you are usually used to in thinking of this, you divide your domain into subpoints. And at each of those points, you define a point. For example, density is this to guys. So each of the points you have rho 1, rho 2, rho 3, etc. That is not the case. Well, that is in some way true, but that is not exactly the structure of our grid in finite volume. The structure of a grid is actually this square cells. The center of the grid is actually where we define quantity, but from the point of view of the numerics, that is not the value of that quantity at the center. That is the volume average value. So we talk of something in terms of cell-centered specification. So this is still cell-centered, but UI is not at the value of Q, the center location. UI is the volume average of the entire distribution. So you might think, okay, what's the difference? You can say call it a volume average, but what if within this domain itself, we have some subgrid restrictions of the dilation? So then U is not constant also. Okay. This can happen, and I'll show you that is what is called grid distribution. Okay, so we start off with this equation and we integrate the fluxes over. So my fluxes are here. So for the finite volume, what is important is to know is to appreciate is you have a volume and the edges of the volume. So for 1D, you have a left edge and a right edge for each volume element. Okay. Now let us integrate this equation both in time and space over this volume element. So the time integral goes from the nth PL and PL plus 1, the next terms of the code. The special integral is just over this small volume equation. Okay. So the fluxes can be integrated in this way. So this del x integrate with the x. This becomes the average flux at this location. But then there is an integral over time remaining. The del u del t. Now you integrate this in terms of the average u. So this is del U del T, and you replace this with del U del T, and U you define it this way. So U is the volume average description of whatever this angle U. It's a volume average description of whatever this value is. You write these equations, and this is the linear first order form. If you go to higher order time stepping schemes, of course, this simple delta T by delta X will not happen. You have to go. If, for example, if you get it on the methods, the right hand side you have to iterate many different times at each step of it. But for simplicity to understand, let's just go first order in time. So after all these manipulations, you can write this equation in this way. What does this give you? It shows you the evolution of the volume average UN. UI at n you have. You need the UI at n plus 1, the next time step. This you can find if you know the fluxes at the cell edges. So important to notice the difference in the spatial locations of where you are defining the conditions. UI, the volume average, associated with the center of the cell. The fluxes at the cell interface. Now, if I just give you a distribution of this U, you can always compute the fluxes. But the fluxes that you will compute would be at the cell center. For example, you went through the fluid equations that were being introduced, right? So what would be the flux of the momentum or the density equation, for example, mass conservation equation? Rho v. That's right. So given if I give you the density discretization and the velocity discretization, always construct the flux. The flux that we construct lies at the center. It's not the flux at the edge. So what do? As Pratik mentioned, we use chemical reconstruction. Well, it is not so simple that you find the flux here and extrapolate here. That does not work. Reconstruction is you know the values of these quantities here. You extrapolate by this reconstruction technique the values of this quantity to the cell interfaces. But you must understand that this is just one cell. There is another cell on the screen. So you take this distribution here. You take your density, extrapolate to here. Similarly, for the cell over here, will also extrapolate another density here. So at the cell interface, where you need to compute the fluxes, there is a problem, right? Because you have two values of density. You have two values of velocity. There it is where you define the Riemann problem. So I guess I'll come to this. Maybe I'm just show you the definition of Riemann problem and then come back. So Riemann problem is, as I was saying, you have something on the left, there's something on the right, at the nth step. When t equals 0, let's rescale our time. What would be its time evolution? That is a Riemann problem. So know the definition now. I'll come back to it later. So before I go into the details, so this is the standard flowchart on the code life. Pluto is not a unique code. There are lots of finite volume codes and increasing by the day. The standard flowchart is set. You first initialize the data at the cell centers. But the data that you initialize, the density, pressure, volume, etc., you have to understand that these are not the values at the center, but volume average quantities. Fine. At t equals to 0, you initialize the cell centers. Then you reconstruct the values of the cell edges. You extrapolate them. It's easier to understand the word extrapolate. So I'm using the word extrapolate, but the technical term is reconstruction. You extrapolate them to the cell edges. As I said, there are just discontinued in cell edges. Then you solve the Riemann problem in the fluxes. The Riemann problem churns out the flux as an input of the solution. Then you integrate in time. So once you know the Riemann problem, for the Godunov scheme, you integrate in time. This is first order, going to second order, third order. You have just, repeat this step one time, depending on the way this thing. You check for output. If the code starts, if it's a time to stop the code, you stop. Otherwise, you keep on going. This is the general flowchart of code. So the first step is actually to reconstruct the values of cell edges. So Pratik has already given you an introduction to it. I'll just briefly gloss over and show you how maybe the 10x from how it's going to. So here, when you start off your distribution, it would actually look like this. So suppose I give you the value at the cell center here, volume average quantity. You have no way of knowing what is the value between these two edges, because that is not given to you. That is the limit of your resolution. Fine. Now, so forget the curved line now. The start of the reconstruction step, you have this discretized regions. We can do one step better. What we can assume is within each cell, now this is subgrid, my quantities are varying according to a polynomial. The order of the polynomial decides the accuracy of the expressions. Okay. So what I must assume, so this I have taken this notations from Andreas' paper. You have to be a bit. This looks a bit complicated with the Jacobian, etc., because this paper was designed for non-Cartesian geometries, cylindricals, spherical, and that's why all others is geometric terms come in, and that's why I have to be careful. The essence of the thing is, you have now this polynomial. So now my reconstruction polynomial looks something like this. But xi ic is some point within this zone. It can be the center of the cell, or it can also be the starting point. Any point. It's just polynomial. And then xi minus xi. Xi is the coordinate between these two edges of the cell. You can go to the pth order polynomial. But what you must ensure that once you integrate over this volume, forget the 1D Jacobian now. Let's make life simple. You integrate over the cell volume and divide by the cell volume. You should recover this average QI that prescribed from your initial conditions or the starting point of a particular place. So this is what we have. This is what we extrapolate. And then what is the reconstruction consisting of? Let's say. So the reconstruction step consists of a stencil of points. So given the order of the polynomials, for example, if you have 3 equals to 1, it's the second order polynomial. Okay. So in the second order, that means you will split the data over 2 points.
The reconstruction polynomial you are mentioning, is it continuous at the equals?
No, this polynomial, okay, it is. That's why the limiters and etc. that Pratik had described. Because what I'm talking about right now is limited to within one cell. All the fits that I'm going to do is limited to within one cell, but it has to know the information about the next. For example, I'll show you the fitting technique, you'll understand better. But the polynomial or the coefficients that we define is one cell. Okay, so for example, as I was talking about, it has a stencil of points. So if it's a second order polynomial, then it will have p equals to 2. It goes in this way. So for a generalized polynomial, you have IL points to the left of the ith cell. So I is the center cell. You have IL points to the left, you have IR points to the right, and plus 1. Total number of points makes a surface. IL plus IR plus 1. Now you have to ensure that the volume averages look something like this, and you can write this equation. So I'm very. Let me slow down a bit. What you have to ensure is the polynomial that you have defined. Now it is not limited once it has a stencil. So the volume averages that you compute out of this polynomial for the cells outside the ith cell should match the volume averages at the I cells. For example, I plus S. S is going from minus I and IR because it's either left or right of the ith cell. So what you must ensure as a method of the scheme is once you do the volume averages of each cell outside the ith cell, it should match the QI. Now, this QI, as I said, is being defined only for the ith cell, but its coefficients should ensure that they also match the volume averages of I plus S, I plus 1, I plus 2, or I minus 1, I minus 2. So this is the constraint we put. So depending on the stencil, this equation can just be expanded in this way. This is just some geometric term and some matrix form. So if I just go back one step, these are the coefficients of the polynomial. If you just take this and you can work it this out as a homework, as just before after this lecture. Some of the equations I show you right now, you just have to take it for word for it. Once you put down pen to paper, this becomes so clear. So you can write this equation at a matrix form like this. So if you invert the matrix, you get the fit coefficients. Okay. So the fact that we are fitting or evaluating these coefficients essentially means we are fitting the polynomial over a stencil of points centered about the line cell. So my entire domain can have 10 cells. So at cell 1, I have a stencil from I have a linear order polynomial to a square order polynomial, I plus 1, I minus 1, and I. In the cell 2, I have I2 plus I3 and I1 in this way. So you can keep on scanning the stencil till you reach the endpoints. So that brings us to another interesting question. What happens at the end? If we need a stencil of points, then we must have some artificial buffer zone where we can extend our stencil. So this buffer zone in Pluto language is called a post. Okay. Fine. So this inversion of the matrix, as you can understand, always requires you to fit the averages at the different cells. So then you need to do the steps of reconstruction at every time step. This is a bit time consuming, so I'll just briefly outline what Pluto does. It's a bit neat trick. Andrea has always refers to bypass the computational costs. So what we have decided then is, instead of that, we just define some weights function. And analytically, it can be shown, is given in the appendix of the paper. This form of the matrix equation is same as this form. So these weights are then, you can see on the right hand side, they are not anymore dependent on the QIs, on the inputs of the density, pressure, etc., etc. So once you compute these weights once, you have to again invert this matrix. Do it at the first step, store the data, that's it. Then you can do the interpolation by so these are the Q plus minus are the values at the edges. So you can find the values of the edges by just the weight function. So this is how it's done in Human. Even if you don't understand this, appreciating this will give you an idea of what we are doing to fit the word. Now, there can be different ways of constructing this fields. The zeroth order. This is first order algebra. The basic one that you can do is no polynomial, just a piecewise constant. So you assign a value here and assume that that value is constant everywhere. So when you choose a reconstruction scheme in Pluto, this is called flat. When you choose a flat reconstruction, this is what you have to choose. Then you can choose a linear order reconstruction scheme. What is linear order? Within each cell, as you can see, that they are not continuous. They may not be continuous. But if they overshoot, as Pratik said, they give oscillatory distributions. So that need massive slopes. So within each cell, they are linear, the linear orders. We can have a parabolic. So this, when you choose this, there is another drop-down menu in the Pluto GUI. It's linear. When you choose linear, you're actually with this. The one that we use as a standard for our production runs is something called the PPM scheme. PPM is nothing but a fancy name for using a lot of parabolic polynomial within itself. It looks something like this.
Like when we code a grid, so the only thing we have are the cell interfaces and the cell center in one place.
Yeah.
So the piecewise constant or any other thing, the values which have been interpolated, we get the values at the center, what we already have. And the interfaces are not somewhere in between.
We don't need that.
You can always find the values.
So if you have a polynomial function, you can always find what is the distribution of functions.
It is not more defined than the cell.
All we need are cell interfaces. For advancing the solution, all we use are cell interfaces. For visualizing the solutions and working and making some sense out of it, we need the ball patterns.
And how's the Vino different from
Same. From the assumptions using the slopes, but essentially it is a scalar.
the coefficients are calculated differently?
Yeah. The way we calculate the coefficients and the slopes are different. Okay, so give an example of what is done in a linear order stream. Okay, it is second order accurate, P equals to N. So what you can do is now you have 2 points stencil. For the ith cell, you can either choose yes. You have finite volume. order of accuracy. The reconstruction scheme, for example, let's say you have to do this accuracy performance at each different level of the scheme, the Riemann solver and the reconstruction. Reconstruction, you can quickly find what polynomial you're using, and then you can find what is this, the difference errors that you can find, and then that is order of accuracy.
So is it the rule of thumb that whenever you have the single order point, you're going to get first order accuracy?
That's right.
So
Yes, so that's the basic definition of the polynomial expansion. It's like a Taylor series expansion. Okay, so you can have either you can fit this description and reconstruct this polynomial either with qi and qi plus 1, or you can go with qi minus 1, as Pratik mentioned, forward and backward differences. We can construct these differences with both. Okay, let me just go directly into the mathematical form, but I wanted to share what is being done. So there is a forward construction and a backward construction. In actual practice, what we do is we use a mix of both slopes. So you can see the forward construction looks like this. So qi is q plus minus on the cell edges. Depends on qi and delta qf, and delta qf is qi plus 1 minus qi. Backward construction is qi plus delta qb. So delta qb is qi minus qi minus 1. What we do is actually a delta q bar. Delta q bar is a function that depends both on the forward slope and the backward slope. And that is related by this function phi nu, or phi nu, whatever you want to call it, which is given by the limiter. That's what we mentioned. So the constraints for choosing the functional form of phi p is there should be 0 gradients at local extreme. You don't want to introduce more extrema that you want to be. It should be symmetric on exchange of forward and backward. And the reconstructed values should be bounded. For example, your qi plus minus 1 should not overshoot the values of the averages of the two either planes. Once you do that, and again, how you choose this phi p is again depends on the level of accuracy. And again, coming back to your question, you can put this choices and then define what is the level of accuracy you are getting for each of the steps.
are we using limiters in the formal accuracy we have written?
Of course. Then it also depends on what form of the limiter you are using. For example, as Pratik also mentioned today, the min mod limiter, the min mod function is something like this. Min mod of delta q and delta qif and delta qip is sine of a and sine of b by essentially an average of both sides. If you do something a bit more complicated, this is not exactly a simple average, but a harmonic. Then it is called a Langmuir limiter. You can clearly see the differences what's happening here. So this is first order plan construction. You can see the actual waveform should look something like this. The first order is spilling over like this. If you do not have limiter, second order without limiter is starting to give you this price because the slopes are not aligned. They're overshooting. Second order with limiter is preserving things. But the question again is, do we always need things to be preserved? I'll tell you something from practical experience. Whenever we land in trouble, we lower the accuracy. Because what will happen is, in case of strong discontinuities, the code will find certain jumps in the fluid variance. Such high contrast actually gives you numerical errors. So as a standard trick, again, there is an option in the Pluto definitions.h called shock flattening. What we do there is, for our standard set of solution all throughout the grid, we have the best of the schemes that are listed. As soon as we face problematic situations, and the definition of problematic situation is numerically coded as when the shock level goes, or the delta P by P, the undivided gradient of the pressure goes more than 3. You can, of course, change it or hard code it in a different way. We jump from here to here. What does that do? It spread out your shock. So the code then, while it is evolving the shock, has some more diffusion for the shock to spread out over some cells. Ideally, you would want to put in more and more cells here to resolve the shock. Once the shock is resolved, the code can go a bit more easily. If the shock is not being resolved, you artificially lower the resolution. Essentially, by lowering the resolution, you resolve the issue.
Are you mentioning that the number of finite volume cells in the first order scheme as well as the shock is more compared to the number of finite volume cells in the second order scheme between the shocks?
No, if the number of finite volume elements cells are larger, that means you are resolving it larger. So second order scheme, you should not think of it in this way. Because as soon as you go to higher number of resolutions, you are increasing the resolution. So that changes the accuracy. But the level, so what do you mean by second order? Given our resolution, how much of the solutions, so suppose you can numerically divide the solution of 4 decimal points. How much of the solution can actually fit? That is the level of accuracy. So as you increase the resolution, of course, you are decreasing the numerical viscosity that is anyway being introduced. But what I'm talking about here is a way of inverting the resolution constraint. For this case, given a fixed resolution, fixed difference of cell elements, you are not resolving it. So had you resolved this, this discontinuity would have been shallow, slightly better. So in that case, the rise is not a delta function like this. It gradually increases over 3 steps, let's say. Since you cannot do that, I'm doing this. Essentially, I'm doing the same thing. I'm again discretizing it into 3 steps. So it's not that you're increasing more resolution elements. You are essentially, by decreasing the accuracy, you are resolving discontinuities better. Okay, so now that we have briefly gone through the reconstruction steps, let us go to the Riemann step. So this is the definition of the Riemann problem. And again, the Riemann problem is actually a mathematical construct. We employ the approximate solutions to the Riemann problem. So Riemann solvers that we have, do not think that we're actually accurately solving the Riemann problem. It can only be done analytically for very constrained 1D systems. Because as I'll show you, it requires a lot of matrix inversions. For multi-D systems, we can't do that. So the basic premise of the problem is you have a discontinuity at a cell edge. You have a left state and a right state. And again, I explained to you why this is the case, because at the cell interfaces, the I-1 has some value as it is approaching. So let's go back to this. So suppose you have done the reconstruction. The polynomial is approaching this cell edge in this way from this cell and giving you some value. Now this polynomial is approaching this cell edge and giving you some value. So there is a natural discontinuity that is in here. So the question is, once we have this, what is the how will the fluid variable evolve with time? Now this ux that I have, these are the general fluid variables. As Pratik mentioned, in the conservative scheme, we work in the conservative variables, which is the density, momentum, and the total edge. So that is what is referred. So what is the time evolution of this? And this we solve by the method of characteristics. Again, I will not spend time on this, but again, wanted you to recapitulate what the method of characteristics for this equation means. Again, you've seen this, but do note how the intermediate steps are, because this is important for you to take over when you solve the Riemann problem. If A is a constant, this is the standard convection problem. Then this is the method of characteristic solutions. Your U is constant along the characteristic. And your X at a given point at a later time is related to the starting point this way. So given the value of U at x0, you can find the value of the U at, so essentially forget the characteristics. So this is how best to visualize it. This is a plane of x and t. You start up from here. You have t equals 0, you have some distribution along x of this variable. Now at later time, what will be the value of the U? What we are finding from the method of characteristics is, for example, if you want to find the value of U at x here and time t here, this will have the value of U that was there at t equals to 0 over here. Okay. So for example, let me ask, what is the, so if this is x, say 10, What is the value of this function u? Because u varies with both space and time. What is the value of the function u at x equals to 10 and time t equals to 1? That will correspond to here, but then this corresponds to a characteristic that is coming from here. So you have to invert it in this. And so essentially, if you find where the characteristic, which characteristic it lies on, you can always draw back to where it was originally, because the u is constant. So that is why f of x naught equals to f of x minus kt. This is the standard expression. Fine. So what we do for the so this is the general theory of the first order hyperbolic equation. Again, Pratik has shown this, but let us again briefly review it. Ut plus fu x. Fu this partial derivative with respect to x, and again partial derivative with respect to t. You convert this. This is del f del x. Convert this into au and ux. Au is a Jacobian matrix. What is this? It's just a simple chain rule. Okay. So now you can recast this in a matrix form. Matrix form is you have a time derivative and your space derivative of this u multiplied by this a. You can find the eigenvectors and eigenvalues of this matrix. Multiply both sides of this equation, which is in the next slide, with the eigenvectors, invert this and get a simple equation in terms of eigenvalues. So this is actually the evolution of the variables along each characteristic. So each of these eigenvalues follow a characteristic. So each of this is actually a simple advection equation that you have, for example, I showed earlier. Okay, so now if you start off with the initial, so now I'm working in the eigenvalues. We can of course transform back to the original fluid frame. So recover the final solution this way. If you know the initial value of W or W1, you can always find what is the time evolution of this is from the fact that along the characteristic. Okay. So this is the basic premise. Again, if you work this out, so I'm telling you, you may think you've understood, but then lunch break when you try to think about it, you feel that you will be confused about it. But when you write these equations down and solve one problem of method characteristics, there are numerous examples on the web. The one that I show, for example, swing wave. I usually show the Gaussian distribution and the Gaussian focus on each other. These are very nice examples to show, and once you do it and invert it numerically, again, looking at it from the display on your screen is one thing. Once you try to code it as Python code, then only you will appreciate what actually goes in and why you do need to have a numerical screen. Okay, so for example, I'm showing here what is the breakup, similar steps for the 1D Euler equation. So if you break, again, these are the simple conservation relations, flow, velocity, pressure. If you break it up into this form, the AW matrix looks something like this. This is the Jacobian matrix, or something like this. The eigenvalues are u minus a, u are u plus a. Again, very intuitive. You have a velocity. You can have three possible combinations of velocity. A is the sound speed. Either velocity plus sound speed, velocity minus sound speed. So if you have information to propagate, given a particular point with a velocity, information can go either along the direction, against it, or there is no sound, just compositing sound. And these are the eigenvectors. So this is something that we have to do for all sorts of different situations. And again, don't be alarmed by what are all these spikes coming up. You have seen the Riemann plan. I'll show you a more complex system of generalized Riemann plan. But what this actually shows is a mathematical construct. What this distribution looks like. So for example, if you, again, going back to the same problem, you start off with this horizontal line at t equals 0, the fluid variables. The question you want to ask is, what is the density at x here and t here? You find what can from this point here, can information travel here? No, because it is limited by the Chomsky. We can only find something in this star region. If I want to find what is here, then it will just be what was there initially, the right-hand state. So in the general solution, you have a left-hand state. So starting from x equals 0, we always in the Riemann problem, the starting point will always recenter our coordinates to x equals 0. So starting from x equals 0, you have a left state, you have a right state, as is the initial discontinuity. And then within that, you have the Riemann fact. So then within these two solutions, so at later time, if I want to ask what is the solution here, is it just a left state? No. Information can propagate from here to here with this. So you have to evaluate what is this rho L star, left star quantities and right star quantities. Again, you might see some familiar notations here, for example, contact discontinuity. Contact discontinuity is where there is a density jump, but there's no pressure jump. So you have a rho left and rho right, but pressure and velocity. Normal components of velocity is conserved. But this is okay, this can be a shock or rarefaction. This can also be a shock and rarefaction. So all the three variables are changed. Fine. So the more complicated looking diagram, this is the general solution of the Riemann problem. This is called the Riemann fan. So the general solution is you start off with the left state and the right state. You find the eigenvectors. You can find the linear combination because they're all dependent. And you start off with this initial solution. So initially, Wi0 at t equals to 0, you had a discontinuity. So for x less than 0, you had some alpha. And x greater than 0, you have some beta. So this is the initial condition. So sum of all the alpha and beta, you get the left state and the right state. Fine. Now, due to method of characteristics, you can always go along each characteristic and have this relation. So W at later time, xt is nothing but x minus lambda. Again, once you appreciate why this is true for the diffraction equation, this will also become clear to you. So x minus lambda t is again alpha I beta I because this is not changing. Except the fact that what is the value? So, for example, the value here, you have to trace it back to its original location. So that is why x naught is equals to x minus lambda. If I go back to slide, this is why I wanted to show this slide. X naught is x minus 80 or x minus lambda. All right. So this is the case that you have this. You had x less than 0, x greater than 0, but x at a t should be x minus lambda t less than 0 and x minus lambda t greater than 0. If this is the case, then you can strictly check that for some eigenvalue, you will have a switch. So there should be a lambda capital I for which x by t is greater than a capital I but less than lambda, smaller than I plus 1. So this full solution, if we get the general solution, actually runs from I equals to 1 to capital I, and then I plus 1 to n. So I to 1 is the beta state of the right-hand state, and I plus 1 to n is the left-hand state. Again, this may feel a bit dense. If I speak about it in 12 minutes, you all understand more than understood. But if you just sit through it and look at it for a while, this becomes very clear to you. Again, Prateek mentioned this, but this is a very nice visualization of what happens at the two interfaces. So if your characteristics at this state looks like this, but the left state actually falling onto the right state, you'll end up with a. In this case, the eigenvectors of the left state have larger values than the right state. Rarefaction, in the same way, the eigenvectors of left have similar values, so the divergence. Okay, so these are the standard criteria for a shock wave, a contact discontinuity, or a rarefaction wave. Why am I talking about this? When you do the SOD test today, you'll find you start off with a discontinuity, it quickly diverges out, and you have the evolution of the discontinuity. Now you might think the discontinuity will just move like this. No, that is not the case. You'll find that the pressure has lowered with a slope like this. If I draw it, start off with like this, you'll find that something like this, the pressure. So this is going this way, which is symptomatic of a rarefaction wave. This is the discontinuity that is proceeding. If you plot the density, it will have to jump at the same state. The density will have an intermediate jump, but the pressure is continuous. That is because that is contact discontinuity. So if you again go back to the full Riemann fan, you will actually have a forward shock, a contact discontinuity, and a rarefaction. You'll see when you see that and work it out, it becomes much more clear to you. Okay, so these are the general solutions of the Riemann, general definition of the Riemann curve. Now, how do we actually go about solving? When do you guys do I have any suggestions? Yeah. So the actual solutions, as you can understand, are quite complicated. Solving the method characteristics for each step, each interface is quite computationally expensive because you have to do a lot of matrix conversions. It is not impossible to do, but it's pretty important. So for that, we employ some approximate steps. Approximate or gloss over some of these things. These steps are called the proximate Riemann solvers, such as the HLL, HLLC, Rho, etc. Why am I mentioning these names? Because these are the schemes you choose in a file called Qt when you choose a Riemann solver. So the full solution of the Riemann solver will actually require you to solve do this matrix, find this matrix, invert it to get also eigenvectors, and for each of these eigenvectors, find the method characteristics and then solve. We'll bypass that. For example, for the HLL, let me go directly to HLL. As I showed you for the 1D Euler, you have three possibilities. You have the contact discontinuity, U plus A, U minus A. We'll remove the contact discontinuity. Let's say that there are only two ways possible. So this is now the level of approximation that is starting to get introduced. We are removing one characteristic completely. We are removing one branch of the solution. That lowers the accuracy, but it is not completely inaccurate. You have a question? Yes.
Why accept contact discontinuity?
Why? Sorry.
Why that one has to match the RHM conditions.
So actually not exactly, except the contact discontinuity, but I misspoke here. Density is not there's no jump the density, but others you have definitive boundary conditions that are. This will become clear when I do HLLC, where I actually introduce the context. Okay, so again for the Riemann fan, then what we do is we just have a slow speed and a fast speed. So then again, these are more mathematical details. Maybe I should briefly skip over because you can just follow the algebra here. But the basic steps, basic steps are you then starting off with the Godunov first order scheme, you integrate the value here, the ux, the fluid quantity that you have between xl and xr, the left state and right state. But this integral you can break up into small steps. So first is where is the foot point of this fan here? That is at TSL. SL is the speed at the left state and SR is the speed at the right state, right characteristic. So you go from XL to TSL, TSL to TSR, and TSR to XR. You just break it up into this. And you write the fluxes accordingly, you get a relation like this. Now, sorry, that was the next step. So here actually what I'm doing is I'm integrating this flux equation. So this total integral, XL to XR, is integrated over the zero component here and the fluxes. So you get one relation like this. This is just from the Godunov first order scheme. Now, what I was talking about, you break it up into this into small segments of the integrals. But then the left-hand side is same. So you just equate this and this. So this is just the broken up integral and equating it to the Godunov flux conservation scheme. If you do that, you will find that you can define an effective average solution of the fluid quantity over this zone where your things are varying. So see, things below TSL actually will remain static, left-hand side state. Things beyond TSR will also remain static, the right-hand side state, because information from any of these points cannot reach these points here. So only region of interest is this. And after some manipulation, you can write a HLL, average HLL description of the fluid quantity, UHLL, as we call it. It can be represented in terms of the left flux, the right flux, the left speed, right speed, the UL and UR. This is UHLL. This is the solution of the Riemann problem with this approximation. Okay. Now you might think, okay, I have the UHLL. Let us just compute the flux here using this UHLL value. That does not give you that good solution. FHLL is not equals to F of. You have to be a bit more careful about doing that. Again, you go back to your short integral. So the basic integral relation, the conservation relation. So starting with the conservation relation, you start from left hand side. So TSL to 0. You can show this is the left and right are both equivalent. I'm showing here the in the book it is there, or you can just work it out yourself. Exercise. So TSL to 0, you can evaluate this integral, and then you will be left with a F0L flux. Okay, and then this flux will be called as the FHL flux. The F0L is same as F0R. So you can just, again, as I said, work it out. So the full solution of the HLL Riemann solver looks something like this. If X is less than TSL, then UL. If X is greater than TSR, then UR. In between, it is UHLL. But for us, what is more important is the flux description. If for 0, if SL is greater than 0, then FL, the left-hand side flux. If the SR is less than 0, negative, then the right-hand side flux. If it is somewhere in between, then use this notation. So again, you may not appreciate all of this unless you work out the mathematical steps yourself. But what are the approximations that we used here? We kicked out the contact distance. From the Riemann fan, we just have 2 approximate fans like this. So how do we define the speeds?
Is there some sort of order of magnitude justification for doing it?
No, it's an ease of convenience.
Okay.
It's numerics. You cannot always define everything by operator. So you can define the errors.
Yeah.
You can quantify the errors. So errors by removing one of the characteristics. Again, I hope that we'll cover this. It will be good also if the listening in, the ones who do the hands-on, take one example, run it in HLL, HLC, TBD. You'll better get a nice picture, maybe the jet example or something like that.
Even the sort.
Even yes. But for the 2D thing problems, you nicely see that for the lower accuracy, you have smooth distribution of density pressure. As soon as you go to HLC, you have a lot of curves. In Helmholtz vortices, etc. Then the Kelvin-Helmholtz law. Okay, so the simplest approximation is UL minus AL and QR plus KR. But this is not always the best. You can have row averages, which is just some mathematical weighting of the left-hand side speed and right-hand side speed. But something called the Einfeld averages. In Pluto, I think have the Einfeld averages. Barker, can you confirm this? I think I confirmed that once. What are the HLL shocks, the shock speeds that we have, wave speeds? Are they Einfeld or the row averages? Row averages? I thought we had the Einfeld averages. Anyway, you can have either of these two. Now, HLL-C solver. This is more mathematically rigorous. So again, I will not go into the steps of the detail, but just give you an overview of what is exactly added onto it, decide what was done in the previous step. Of course, you have the finally stability. Now you are dividing your regions into a few different steps. You have UL. Between the left state and the contact discontinuity, you have a UL star. Between contact discontinuity and the rightmost wave, you have U star R. And then you have the right state. This becomes very complex now. Earlier, you had the initial left and right values. You have just some intermediate zone where you could construct things more easily. Now you have jumps in the fluid solutions at each of these Riemann fans. So these are actually jumps in the fluid solution. So across each of these characteristics, you must apply the Rankine Decorn conditions in that. Again, the very premise of the scheme is same. You have to identify a QHLL value. This now becomes more complex because you have the left state and the right state and a combination of the star regions. Then this is the approximate scheme of the HLL-C solution. If X is less than SL, of course, you have UL and UR here. Then you have to evaluate what is the U star L and U star R. But the fluxes will also have to be evaluated. For example, you actually go to the details of it. Your pressure, so across the contact discontinuity over here. So between here and here, there will be a jump in fluid variables. Between the U star R and U R, all fluid variables will change because this is a shock. This is a contact discontinuity. Here, the density and the normal component of the velocity is constant. So the UL star and U star R is just U star. Pressure is also constant. But then you have the variation of other components. So you have to, working with this, you have a couple set of equations. You have to solve them. You have to find what are the speeds of the stars, etc., and then solve it. Again, these are all textbook information. You can go into the details of it if you want. So this is the HLLC solver. For standard applications, we actually use this. There is another solver. Okay, before Lax Friedrichs, I just come to the row solver. So, okay, maybe the Lax Friedrichs is better because O is a different formality. So this is, again, Lax Friedrichs is again a very diffusive, lower order accuracy solver. And you can see the drastic approximation that I'll make here. This is the HLL flux, the HLL, just two waves. The Lax Friedrichs will just do away with one more way. Just identify the maximum speed and say that their SL is minus S and SR is plus S. Again, the level of approximation is something that you should appreciate. You take your HLL flux, put it in, you get some value of the fluxes. These are not completely inaccurate though. If your fluid is responding to some perturbations, it will try to go with the maximum speeds. Of course, the maximum speed will reach first. The later stages are perturbations and higher order perturbations, other waves speeds are also spotted. So if you're just interested in what is the immediate response, like a strong shock, this is not too bad. But you lose the internal variations of the pressure density. And that's why things are smooth except at strong. Row solver has a slightly different approach to solving this. So for now, what we have been doing is starting off with the characteristic solutions and then making an approximation on the number of characteristics you are considering. Row is slightly different. Start out with this basic equation. Now this AU matrix, the Jacobian matrix, these are dependent on fluid quantities. Row solver, you assume that this is constant. This makes life a lot more simpler. Now because this becomes simple advection equations, you can write them in terms of the just expansion of the eigenvectors. Right? But then there are other implications to it. Again, I'll not go to the details of row solver. Again, textbook are there to tell you the details of it. But since this is, we're not excluding any characteristic, row solver is more accurate than the others. Of course, you are still making an assumption here. So the level of assumption is slightly different on a different dimension than the others, but this is more accurate. So if you want to test a problem and want to find out higher accuracy, we use row. But as I said, in practical application, for example, you are following a supernova explosion, multiple supernovae colliding with one another, strong shocks going and merging with each other. This kind of solve this quick first. Okay, so that I think finishes my set of slides for this. Any questions now, or you need to think about it and let things settle down?
So in the reconstruction step, I don't understand why the symmetry condition between forward and backward thing comes.
Yeah, because if you just switch the forward and backward, if you get different slopes, then your basic assumption is correct. If you want to have a continuous distribution, whether you take a forward step or a reverse step, it should not matter. So if that is affecting your slope of the solution that you're getting, then it's not a good thing.
Okay.
Just to be clear, the initial Riemann problem was we had a value of the conservative variables on one side, some values, another values on the other side. And finally, we are finding that F, the LLC, is the flux of this.
That's right.
So, in this part, we are assuming that it has a single.
Which part?
I don't know, it's not the right part. It has a single value.
No. The discontinuity is still there because you cannot escape this setup. Sorry. Or the Lax matrix? No, I'm saying that you cannot escape this setup. This discontinuities will always be there. What we want to find out is at t equals 0, if this is a discontinuity, what would be the value of the fluid quantities at this line to finite t? That is the basic premise of the Riemann problem. So given a shock, Riemann problem essentially a shock. Given a shock and given a conservation relations, how will the fluid variables evolve with time? For our purpose, all we are interested in is the solution of x equals 0. But Riemann problem gives you full solution.
But like in the Riemann problem which we define has a constant value on the one side.
Constant value on one side and constant value on this side, but at later stages you have
That's the initial stage. Yeah, can't be that's a constant that's a constant.
it's not a no, it's not a piecewise constant. This is a constant, not a constant value. This is a value at the left edge. So you have a value here. As you take a limit towards this edge, what is the value here? It's not that this is piecewise constant all through. So I have drawn this as a evil state. So it could be like this, approaching here, and this approaching like this. It is the limit. So whatever distribution of u is on the left hand side, limit this x goes to I plus half. What is the value?
And like regardless of the optimizations we make for the Riemann solver, the fact that we have to invert matrices for the reconstruction step just remains a
Straight. But as I said, you can do it in a bit of a nice trick, and you don't have to switch. This just depends on the grid structure. There is no input from any fluid variable here. So giving the fluid variables call, your weight function does not change.
Are there methods which use like different basis functions for the expansion, or
What do you mean different functions?
so
Some beyond polynomial?
yeah,
You can, but it increases the complex.
yeah.
So very much simpler.
Yeah.
Also, you can go from a Taylor expansion part of so.
Yeah.
In the room solver, we are assuming like a quantity of the flux constant. So yeah, so, like
We are considering that the way the matrix values are constant. The Jacobian is constant. Yeah, this Jacobian is constant. So what is this Jacobian? For example, in the 1D Euler, what was it? This. These can evolve with time, right? These are fluid quantities. We are just taking it to the same value at t equals 0. In that way, it's quite a drastic approach to as well.
like to capture some transient phenomena. So initially, room solver will not give the good answer, but later time it
No. This is solved every time step. So this is not t initial because this is the tn. From tn and from tn plus 1. I'm assuming that whatever values are here, they are constant. So if you expand this time series, if the time evolution of these are slower compared to the dynamical speed, anyway, the fluid dynamical timescales are defined by how these things are varying anyways. If you consider that the fastest varying quantity is not varying very fast compared to your time step, then this is a good approximation. Okay.
Let's thank Dipanjan for